For most of our lives, Pluto was simple. The ninth planet, small, cold, far away. And then, in 2006, it was quietly stripped of its status. Not a planet anymore. Just another frozen object at the edge of the solar system. To most people, that was the end of the story. Pluto became a punchline, a world we were told no longer mattered. But something strange happened next. In 2015, a spacecraft flew past Pluto for the first, and possibly only, time in human history. And the images it sent back didn't match the story we'd been told. There were mountains rising where none should exist, ice that appeared to be moving, a vast, bright heart etched into the surface, and hints that beneath all that frozen darkness, liquid water might still exist. Pluto wasn't quiet, it wasn't dead, it wasn't simple, which leaves us with a question that science still hasn't fully answered. How can a world this small, this cold, and this distant still be alive? Everything we thought we knew about Pluto was wrong. But before we understand why Pluto shocked scientists, we need to remember what we once believed Pluto was. For most of the 20th century, Pluto lived in a very quiet place in our minds. It was the ninth planet, the last one, a small, distant dot at the edge of the solar system. It appeared at the end of every textbook diagram, at the tail of every mnemonic sentence we learned in school. Always faint, always far away, but officially complete. Pluto was discovered in 1930, at a time when astronomy was limited by glass lenses, photographic plates, and long nights of patient observation. Astronomers weren't looking for Pluto itself. They were searching for something much larger. For years, scientists believed there had to be a massive, unseen planet beyond Neptune. Something big enough to disturb the orbits of Uranus and Neptune in subtle ways. They called it Planet X. At the Lowell Observatory in Arizona, a young astronomer named Clyde Tombaugh was tasked with scanning the sky again and again, comparing photographic plates by hand. Night after night, he searched for anything that moved, and eventually, he found it. A tiny point of light, faint, slow, but clearly shifting against the background of fixed stars. That object was Pluto. At the time, Pluto fit what we thought a planet was supposed to be. It orbited the sun, it seemed isolated, and most importantly, it was all we could see. What no one realized yet was that Pluto wasn't alone. It was simply the brightest thing in a region we hadn't discovered. From Earth, Pluto is extraordinarily difficult to observe. Its diameter is only about 2,377 kilometers, smaller than our moon. Its mass is just 0.2% of Earth's. Even at its closest, Pluto is more than 4.3 billion kilometers away. At its farthest, that distance stretches beyond 7.5 billion kilometers. At those distances, Pluto doesn't look like a world. It looks like a pixel. And for decades, that pixel told us almost nothing. So scientists filled in the blanks. They imagined Pluto as a frozen leftover, a cold, inactive relic from the early solar system, too small to hold heat, too distant to change, and that assumption felt reasonable. Small worlds cool quickly. Without strong gravity or constant energy, they go quiet. For nearly 70 years, Pluto was called a planet, not because we truly understood it, but because we didn't yet understand its neighborhood. As telescope technology improved near the end of the 20th century, something unexpected happened. Astronomers began finding other icy objects far beyond Neptune. Some were nearly as large as Pluto, some even larger. What we once believed was empty space turned out to be crowded. This distant region became known as the Kuiper Belt, a vast ring of frozen remnants left over from the solar system's formation. Pluto wasn't standing at the edge of nothing. It was standing inside something. And that realization quietly undermined everything we thought we knew. If Pluto was a planet, then what about all the others like it? Were we ready to add dozens of new planets? Or had our definition been wrong all along? By the early 2000s, Pluto's status was already fragile. Its orbit was steeply tilted, about 17 degrees compared to the relatively flat plane of most planets. Its path was stretched into a long ellipse, sometimes carrying it closer to the Sun than Neptune. Pluto didn't behave like the orderly worlds we were comfortable with. But culturally, Pluto was still a planet. Familiar. Comforting. The final piece of a system we thought was complete. And that emotional attachment would make what came next feel personal. Because in 2006, scientists didn't change Pluto. They changed the rules. Pluto didn't fall out of favor because it failed science. It fell out of favor because science finally asked a harder question. Pluto didn't change. Its orbit stayed the same. Its distance from the Sun remained unchanged. Its frozen surface was just as cold and distant as it had always been. What changed was the language we used to describe it. In 2006, the International Astronomical Union made a decision that quietly reshaped astronomy. For centuries, the word planet had been flexible. Anything that wandered across the sky against the background of stars once qualified. Over time, the definition narrowed, but it was never precise. By the early 2000s, that vagueness became a problem. Astronomers were discovering more and more objects beyond Neptune, icy worlds. Some nearly as large as Pluto, some strikingly similar. If Pluto was a planet, then many of these objects would have to be planets too. So scientists decided to draw a clear line. They proposed 3 criteria. A planet must orbit the Sun. It must be massive enough for gravity to shape it into a sphere, and it must have cleared its orbit. That last requirement caused the controversy. To clear an orbit doesn't mean emptiness, it means dominance. Earth rules its neighborhood. Jupiter controls everything around it. Over billions of years, these worlds became gravitational authorities. Pluto never did, not because it failed, but because of where it lives. Pluto resides inside the Kuiper Belt, a vast region beyond Neptune filled with frozen remnants from the solar system's formation. In that environment, Pluto is not unique. It shares space with countless other icy bodies, some smaller, some close enough in size to matter. Pluto doesn't dominate its neighborhood. It belongs to it. Under the new definition, that distinction mattered. So Pluto was reclassified, not removed, not erased, simply renamed. It became a dwarf planet. To the public, it felt like a demotion, like something familiar had been taken away. But scientifically, nothing about Pluto became less important. The change wasn't about value, it was about precision. Astronomy wasn't shrinking the solar system, it was revealing how crowded the outer regions really are. And that realization was uncomfortable. Because Pluto wasn't just an object in space, it was part of childhood diagrams, part of how many of us first imagined the solar system. The mistake wasn't redefining Pluto. The mistake was assuming that smaller worlds couldn't surprise us. By removing Pluto from the traditional list of planets, scientists unintentionally did something else. They removed expectations. Pluto was no longer required to behave like a familiar planet. It was free to be something stranger, something different. And that raised a far more interesting question. If Pluto wasn't simply a small, failed planet, then what kind of world was it really? That question would remain unanswered for nearly a decade, until a spacecraft, launched the very same year Pluto lost its title, finally arrived to see it up close. To understand what Pluto truly is, science would have to stop debating definitions and go there. In 2006, while Pluto was losing its title on Earth, a very different story was beginning far from public attention. A spacecraft was being prepared for a journey no mission had ever attempted before. Its destination was Pluto. Its challenge was distance. At the time, Pluto lay more than 4 billion kilometers from Earth. A conventional spacecraft would take decades to reach it. Waiting that long was not an option, so engineers designed something different. The mission was called New Horizons. Instead of building a heavy spacecraft meant to slow down in orbit, they built something light and efficient, designed to move fast, conserve energy, and survive for years in deep space. On January 19, 2006, New Horizons was launched from Cape Canaveral aboard a powerful rocket. Within just 9 hours, it passed the orbit of the Moon. That moment quietly set a record. What took Apollo missions 3 days, New Horizons did before the day was over. But even that speed wasn't enough. To reach Pluto within a human lifetime, the spacecraft needed help. 1 year later, it approached Jupiter, not to study it in detail, not to stay. Instead, New Horizons used Jupiter's immense gravity to reshape its path. As the spacecraft swept past the giant planet, it borrowed a small amount of Jupiter's orbital energy. That brief encounter dramatically increased its speed and redirected it outward, toward the distant edge of the solar system. From that point on, the course was set. There would be no braking, no turning back. New Horizons was not built to stop at Pluto. It would pass by once, collecting as much data as possible in a narrow window of time, and then continue onward into darkness. This made every detail critical. The spacecraft would be traveling so fast that even a small mistake could end the mission. A fragment of dust, a miscalculated angle, a failure in timing. Any of these could mean silence. After the Jupiter flyby, New Horizons entered a long, quiet phase. For most of its journey, the spacecraft was placed into hibernation. Its systems powered down, its instruments resting, drifting farther from the sun each year. Occasionally, it would wake. Engineers would check its health, make small adjustments, then let it sleep again. As the distance grew, communication slowed. By the early 2010s, radio signals took more than 4 hours to travel one way between Earth and the spacecraft. There was no real-time control. Everything depended on decisions made years earlier. As 2015 approached, tension returned. Pluto was still largely unknown. Its moons were small and irregular. There were concerns about unseen debris surrounding the system, particles that could damage the spacecraft at high speed. The margin for error was thin. On July 14, 2015, New Horizons passed Pluto at a distance of about 2,500 kilometers. It did not pause. It did not turn. For hours after the flyby, Earth heard nothing. The spacecraft was busy, focused entirely on Pluto, storing images and measurements on board. Then, finally, a signal arrived. Short, simple. We're alive. The mission had survived. The data would take months, then years, to fully reach Earth. But already, one thing was clear. For the first time in human history, Pluto was no longer a distant point of light. It had become a place. And when the first images finally arrived, they revealed a world no one had imagined. When the first images from New Horizons finally arrived, they didn't rush in all at once. They came slowly, pixel by pixel, line by line. At first, Pluto was still just a blur, only slightly sharper than anything humanity had ever seen before. But with each new frame, something unexpected began to take shape. This was not a uniform ball of ice. Light regions appeared beside darker ones. Sharp boundaries cut across the surface. Pluto had contrast. And then one feature emerged that immediately stood out. A vast, bright shape on the surface, so distinct that it almost looked artificial. Scientists named it Tomball Regio, the heart of Pluto. From a distance, the heart was unmistakable. Two pale lobes of ice set against darker terrain. It didn't look ancient. It didn't look heavily scarred. It looked young. As resolution improved, attention shifted to the left side of the heart. What scientists saw there changed everything. A massive, smooth plain of ice, nearly free of impact craters. This region became known as Sputnik Planitia. It stretches hundreds of kilometers across, roughly the size of Texas. And unlike most surfaces in the solar system, it shows almost no signs of long-term bombardment. That detail mattered. Craters accumulate over time. The more you see, the older a surface usually is. Sputnik Planitia had almost none, which meant this landscape was geologically young. Something had resurfaced it, recently on cosmic timescales. As scientists studied the images more closely, another pattern emerged. Sputnik Planitia wasn't just smooth. Its surface was divided into enormous, polygon-shaped cells, each tens of kilometers wide. They resembled cracked ice or the surface of a slow-moving liquid. But Pluto is far too cold for liquid water. At surface temperatures near 229 degrees Celsius, water ice behaves like solid rock. Instead, this plain is made primarily of frozen nitrogen, and nitrogen ice behaves differently. Under Pluto's weak gravity and extreme cold, nitrogen can slowly flow. It can rise when warmed and sink when cooled. What New Horizons had captured were signs of convection. Warm nitrogen ice, heated from below, was slowly rising. Cooler ice was sinking. The entire plain was circulating, moving at a pace measured in centimeters per year. This was the moment everything changed. Because convection requires energy, and energy requires heat, somewhere beneath Pluto's surface, there had to be a long-lasting source of warmth, enough to keep this process active over millions of years. According to everything scientists once believed, this should not have been possible. Pluto is small. Its mass is only a fraction of Earth's. Worlds this size were expected to cool quickly and fall silent. Pluto did not. The edges of Sputnik Planitia revealed even more surprises. Towering mountains rose abruptly from the smooth plain, some reaching 3 to 4 kilometers high. These were not rocky mountains. They were made of water ice. At Pluto's temperatures, water ice is strong, hard enough to behave like granite on Earth. These mountains likely floated on softer nitrogen ice below, like massive icebergs frozen in place. Beyond the heart, the landscape grew darker and more complex. Jagged terrain, long ridges, regions stained deep red by complex organic molecules formed by sunlight interacting with surface ice. Pluto was not just active, it was diverse. Every assumption that had shaped Pluto's reputation began to collapse. This was not a leftover fragment, not a static relic from the solar system's formation. It was a world with layers, with motion, with an internal story still unfolding. And perhaps the most striking part of all, none of this had been predicted. not the heart-shaped plain, not the absence of craters, not the slow circulation of ice. Pluto hadn't merely surprised scientists. It had exposed a deeper mistake: the belief that small worlds must be simple. Pluto was small, but it was anything but simple. By the time the full dataset began arriving, one truth was unavoidable. If a world this distant, this cold, could still be geologically alive, then Pluto was no longer an exception. It was a warning that the outer solar system might be far more active and far more complex than anyone had imagined. Pluto wasn't just alive on the surface. Something beneath it was still working. After the shock of Sputnik Planitia, scientists began to look beyond Pluto's heart. What they found erased the last traces of an old assumption. Pluto was not just active in one place. Its entire surface told a story of motion. Towering mountains rose from the icy plains, some reaching 3 to 4 kilometers in height. That alone was astonishing. Their existence alone proved something critical. Pluto's surface had not been static. It had been shaped, lifted, reworked. Then came the glaciers. Along the edges of Sputnik Planitia and across nearby regions, scientists identified vast flows of ice slowly creeping across the landscape. These were not glaciers of frozen water. They were glaciers of nitrogen ice, mixed with carbon monoxide and methane. Over time, measured not in days or years, but in tens of thousands of years, these ices had flowed downhill, pooling in low-lying regions. Some glacier tongues stretched for dozens of kilometers. Others piled up against mountain ranges, forming frozen ridges. Glaciers require movement. Movement requires energy. Once again, Pluto refused to behave like a dead world. But perhaps the most surprising features of all were the structures that looked unmistakably volcanic. On Pluto, they are called cryovolcanoes. Instead of molten rock, cryovolcanoes erupt with icy material, water, ammonia, or other volatile substances that behave like lava under extreme cold. Two candidates stood out immediately: Right Mons and Kaladzi. These structures were enormous. Right Mons rises roughly 4 kilometers above its surroundings and spans more than 150 kilometers across. It has a broad, dome-like shape, a central depression, and flanks marked by irregular flows. It looks nothing like an impact crater. Kaladzi is similar: large, elevated, and oddly shaped, with surface features suggesting repeated episodes of material rising from below. These were not random piles of debris. They had structure, symmetry, history. If these features are indeed cryovolcanoes, they point to something extraordinary. They suggest that material from Pluto's interior has reached the surface, not once, but multiple times. That requires heat, sustained heat. And that raises a difficult question. Where does the energy come from? Pluto is too small to retain much heat from its formation. Radioactive decay alone should not be enough to keep it active after billions of years. And yet, the evidence was undeniable. Mountains, glaciers, possible ice volcanoes. Pluto was not a fossil. It was a system. One explanation is that Pluto may have retained heat far more efficiently than expected, perhaps insulated by layers of ice that slowed cooling over time. Another possibility is even more intriguing. Pluto may still have a subsurface ocean, a layer of liquid water kept warm by internal heat and insulated by thick ice above. If such an ocean exists, it could help explain the surface activity. It could provide the energy needed to drive convection, to fracture the crust, to feed cryovolcanic eruptions. Nothing about this was supposed to happen on a world so small. And yet, every new line of evidence pointed in the same direction. Pluto was not frozen in time. It was evolving, slowly, quietly, but persistently. The old idea of Pluto as a failed planet, a leftover fragment, a cosmic afterthought, could no longer survive. Pluto wasn't trying to be a planet like Earth or Mars. It was following its own rules. Rules shaped by extreme cold, by strange chemistry, by an environment unlike anything closer to the Sun. And that realization carried a powerful implication. If Pluto, a world once dismissed as insignificant, could support mountains, glaciers, and eternal activity, then size alone could no longer be used as a shortcut to understanding. Small worlds could be complex. Cold worlds could be alive. Pluto didn't just challenge our definition of a planet. It challenged our understanding of what a world could be. And if Pluto still has heat beneath its surface, then its story may be far from over, at the edge of the solar system, where sunlight is faint and warmth is scarce. Pluto should not have an atmosphere. That was the assumption. A world this small, this cold, this distant, should have lost any gases long ago. And yet, when New Horizons arrived, Pluto revealed something quiet and unexpected. A thin, delicate atmosphere. Not thick, not turbulent, but real. Pluto's atmosphere is composed mostly of nitrogen, with traces of methane and carbon monoxide. It is incredibly thin, far thinner than Earth's, even thinner than Mars. But it exists, and it changes. As New Horizons passed behind Pluto, its instruments watched sunlight filter through this fragile envelope of gas. What they saw was breathtaking. Layer upon layer of haze, more than 20 distinct layers, stacked above Pluto's surface like a cosmic fog. Each layer gently curved around the planet, glowing faintly in the distant sunlight. These hazes were not clouds. They were made of tiny particles formed high in the atmosphere, where ultraviolet light from the sun interacts with methane and nitrogen. That energy breaks molecules apart and then allows them to recombine into more complex forms. Over time, these reactions produce tholins, complex organic molecules. Tholins are not signs of life, but they are the building blocks of chemistry that, elsewhere, can lead to life. As these particles grow heavier, they slowly drift downward, settling onto Pluto's surface. There, they stain the ice with deep reds and browns. This is why Pluto looks the way it does. Not gray, not white, but colored, painted by chemistry. The red regions on Pluto are not scars from impacts. They are the result of ongoing atmospheric processes, quiet, continuous, and ancient. And Pluto's atmosphere does something else that no one expected. It breathes, not in minutes or hours, but over centuries. Pluto follows a long, elliptical orbit around the Sun, taking 248 Earth years to complete a single revolution. During that journey, Pluto's distance from the Sun changes dramatically. Sometimes, it is close enough for surface ice to warm and sublimate, turning directly from solid into gas. At other times, it drifts so far away that the atmosphere begins to freeze and fall back onto the surface as frost. Pluto's atmosphere does not stay constant. It expands, it contracts, it rises from the ice, and then settles back down. A slow planetary breathing cycle, measured in generations. This process connects Pluto's surface to its sky. Nitrogen ice evaporates into gas. Gas cools and condenses back into ice. Methane migrates across the surface, reshaping landscapes over time. Nothing is still. Even here at the edge of the Sun's reach, Pluto remains active. The atmosphere also interacts with Pluto's geology. As nitrogen freezes and thaws, it can erode surface features, soften edges, and feed glaciers. The sky and the ground, are not separate systems. They are one. This delicate balance exists only because of Pluto's unusual conditions. Too small to hold a thick atmosphere permanently. Too cold to behave like a typical planet. Yet active enough to maintain a complex exchange between surface and sky. It is a world balanced on a knife's edge. Change the temperature slightly, and the atmosphere collapses. Change the orbit slightly, and it thickens again. Pluto lives in that narrow zone between presence and absence. And perhaps that is what makes it so compelling. Because it reminds us that atmospheres are not guaranteed. They are temporary. They depend on distance, on chemistry, on time. Pluto shows us a version of a planetary atmosphere stripped down to its essentials. No oceans, no storms, no winds we could stand in. Just molecules, light, and slow motion. In its hazes and colors, Pluto preserves a record of processes that once shaped many worlds, including our own. Long ago, Earth's atmosphere may have looked more like this. Thin, chemically active, evolving under a young sun. Pluto is not a mirror of Earth, but it is a reminder that even in the coldest, darkest places, chemistry does not stop. It adapts. It continues quietly, layer by layer, over unimaginable spans of time. And in that silence, Pluto breathes. If Pluto can maintain an atmosphere and reshape itself beneath it, then its place in the solar system deserves a second look. When we talk about Pluto, we often imagine a solitary world at the edge of the solar system. Small, cold, alone. But Pluto has never truly been alone. From the moment it was discovered, Pluto has shared its journey with a companion, one unlike any other in the solar system. Its name is Charon. Charon is not a typical moon. It is enormous. With a diameter of about 1/200 kilometers, Charon is roughly half the size of Pluto itself. That size difference changes everything. Most moons are tiny compared to their planets. Earth's moon, large as it is still only about 1/4 Earth's diameter. Charon is different. It is so massive relative to Pluto that the two bodies do not orbit in the usual way. Instead of Charon circling Pluto like a moon around a planet, both worlds orbit a shared point in space, a point called the barycenter. And in this case, the barycenter lies outside Pluto's surface. That detail is crucial. It means Pluto is not the central anchor of the system. It means Pluto and Charon move together. They dance. This makes Pluto and Charon a binary system. Two worlds locked in a gravitational partnership. From Pluto's surface, Charon would appear enormous in the sky. It would never rise or set. Both Pluto and Charon are tidally locked to each other. They always show the same face. One hemisphere of Pluto permanently faces Charon. One hemisphere of Charon permanently faces Pluto. Their relationship is intimate and unchanging, measured not in days, but in billions of years. When New Horizons approached this system, Charon revealed its own surprises. At first glance, Charon looks different from Pluto. Its surface is darker, more uniform, less colorful. But it is far from simple. Charon is covered in deep canyons and fractures, some stretching for hundreds of kilometers and plunging several kilometers deep. These are among the largest known fractures in the solar system. They suggest that Charon's interior once expanded, likely due to freezing of an internal ocean long ago. As water froze, it expanded. The crust cracked. Charon tells a story of ancient change. At its north pole, Charon displays a striking dark red region. This coloration likely comes from material originating on Pluto itself. Methane escaping Pluto's atmosphere can drift through space, fall onto Charon's cold surface and be chemically altered by sunlight. Over time, that process produces dark organic compounds, similar to the tholins that color Pluto. This suggests that Pluto and Charon are not isolated worlds. They exchange material. Pluto's atmosphere does not simply escape into space. Some of it becomes part of Charon. In this way, the two worlds are connected, not just by gravity, but by chemistry. Their origin story is just as remarkable. The leading hypothesis is that Pluto and Charon formed after a massive collision early in the solar system's history, a giant impact. Debris from that collision coalesced into Charon, leaving both bodies locked together ever since. This scenario explains their unusual sizes, their shared orbit, their synchronized rotation. Pluto and Charon are not a planet and a moon. They are the survivors of a violent beginning. Together, they form the heart of a small system of moons: Styx, Nix, Kerberos, Hydra. Tiny companions orbit farther out, remnants of the same ancient collision. What makes this system special is balance. Charon stabilizes Pluto's rotation. It may influence internal stresses. It shapes how Pluto's surface and atmosphere evolve over time. Some models suggest that the gravitational interaction between Pluto and Charon could have helped maintain internal heat, especially early in their history. Their partnership may have prolonged Pluto's geological activity. Seen this way, Pluto's complexity does not belong to Pluto alone. It belongs to the system, a pair of worlds bound together, shaping one another over billions of years. This challenges another long-held assumption, that small worlds are simple. Pluto and Charon show that complexity does not require size. It requires interaction, gravity, time, history. The Pluto-Charon system is not a scaled-down version of something closer to the Sun. It is its own category, a reminder that the solar system is more diverse than our labels suggest. When we look at Pluto now, we are not looking at a single object. We are looking at a relationship. Two worlds locked in a slow, permanent orbit, circling not just each other, but a shared past. And if one small system at the edge of the solar system can be this rich, then perhaps Pluto is not an exception. Perhaps it is an introduction. And beyond Pluto and Charon, even more distant worlds are waiting. Worlds that may share the same hidden complexity. After the flyby, New Horizons did not turn around. Pluto and Charon slowly faded into the darkness behind it. Their surfaces, their mountains, their atmosphere, all now part of history. But the mission was not over. New Horizons was still moving outward, still carrying momentum borrowed long ago from Jupiter, still traveling into a region few spacecraft had ever explored. Beyond Pluto lies the Kuiper Belt, a vast, dimly lit ring of space extending far past Neptune, filled with icy remnants left over from the solar system's formation. For decades, this region was mostly theoretical. Astronomers knew it had to exist. Models predicted it. But it remained largely unseen, too distant, too faint, too cold. Pluto was once thought to be alone out there. Now we know it is only one member of a much larger family. Thousands, perhaps millions, of small, icy worlds orbit the Sun in this distant belt. Some are larger than mountains. Some rival Pluto itself. All of them are ancient. Unlike planets closer to the Sun, Kuiper Belt objects have changed very little since they formed. They are not shaped by volcanoes of molten rock. They are not eroded by water or wind. They are preserved, frozen in time. In 2014, scientists using space-based telescopes identified a small object deep within the Kuiper Belt, one whose orbit New Horizons could reach with a modest course correction. The target was originally known by a long catalog number. Later, it was given a name, Arakoth. This object would become the most distant world ever explored up close. On January 1st, 2019, New Horizons flew past Arakoth at a distance of just over 3,500 kilometers. What it revealed was unlike anything seen before. Arakoth was not round. It was not smooth. It looked like two objects gently pressed together, forming a flattened, snowman-like shape. This structure is known as a contact binary, two lobes that likely formed separately, then slowly drifted together and merged at extremely low speeds, so low that neither object shattered. This was not a violent collision. It was a quiet meeting. Arakoth showed no signs of compression, heating, or geological reworking. Its surface was smooth, uniform, untouched. It had remained almost exactly as it formed, over 4.5 billion years ago. This made Arakoth something extraordinary. A time capsule, a direct glimpse into the earliest stages of planetary formation. While Pluto tells a story of complexity, heat, and change, Arakoth tells a story of stillness. It shows us how small worlds began, before gravity, heat, and collisions reshaped them. Together, Pluto and Arakoth represent two ends of the same spectrum. One evolved, one preserved. Both are equally important. The Kuiper Belt is filled with objects like Arakoth, cold, ancient, chemically primitive. They formed far from the sun, where temperatures were low and materials moved slowly. In this environment, growth was gentle. Instead of smashing together violently, particles stuck, pebbles accumulated, lobes formed. The Kuiper Belt may preserve the original architecture of the solar system better than any other region. Studying these worlds helps scientists answer fundamental questions. How did planets begin? How quickly did they grow? What materials were present in the outer solar system? The answers are not found in planets like Earth or Jupiter. They are found in these quiet, distant objects. New Horizons was never designed to stop. After Arakoth, it continued outward, still healthy, still listening, still sending back data from a region beyond Pluto. Every measurement, every faint signal, expands our map of the solar system. What once seemed like empty space is now recognized as a complex frontier, not barren, not silent, but filled with worlds, each carrying a different version of the past. Pluto showed us that small worlds can be active. Arakoth showed us that small worlds can be ancient. Together, they tell a larger story. The outer solar system is not a graveyard of leftovers. It is an archive, a record of how worlds form, change, and sometimes remain exactly as they began. As New Horizons continues its journey, it carries with it a simple message. The farther we look, the older the stories become. And sometimes, to understand how everything started, we have to travel to the very edge and listen carefully to what the coldest worlds still remember. After Pluto, the journey didn't end. It revealed just how much of the solar system we had barely begun to understand. For a long time, Pluto was defined by a title, the 9th planet. Then suddenly, not a planet at all. That change sparked debate, disappointment, even anger, as if something important had been taken away. But after everything we have seen, one truth becomes clear. Pluto never needed a title to matter. What New Horizons revealed was not a failed planet or a demoted world. It revealed something far more important, a lesson. Pluto showed us that our old shortcuts don't work anymore. For decades, we believed that size determined significance, that small worlds were simple, that distant worlds were frozen and finished. Pluto quietly dismantled all of that. It showed us mountains made of water ice, standing kilometers high, glaciers flowing across plains of frozen nitrogen, possible ice volcanoes reshaping the surface, a thin atmosphere that rises and falls over centuries, chemistry painting the surface in reds and browns, and clues pointing to a hidden ocean beneath the ice. None of this fit the old picture. Pluto did not behave the way a dwarf planet was supposed to behave. But perhaps that expectation was the real mistake. Pluto didn't fail to meet our definitions. Our definitions failed to describe Pluto. Science advances not by protecting familiar categories, but by letting observations force new ones. Pluto forced us to admit something humbling, that even after centuries of astronomy, we still misunderstand entire classes of worlds. And that misunderstanding matters. Because Pluto is not alone. It belongs to a vast population of icy worlds in the outer solar system, worlds shaped by cold, chemistry, and time. If Pluto can be complex, active, and layered, then many of these distant bodies may be as well. Pluto didn't just teach us about itself. It taught us how incomplete our mental map of the solar system had been. There is another reason Pluto still matters. It reminds us how exploration really works. Pluto was not understood from Earth, not through telescopes, not through equations alone. It was understood because we went there. Because a small spacecraft crossed billions of kilometers, flew past once, and sent back a few precious moments of data. That was enough to overturn decades of assumptions. In that way, Pluto is a reminder of how fragile certainty can be. What we believe today often rests on limited evidence, and what feels settled can change the moment we look closer. This is not a weakness of science, it is its strength. Pluto also carries a quieter message. That importance does not require attention. For most of human history, Pluto was invisible. For most of the universe's history, it has existed in darkness and silence. And yet, beneath that silence, it has been active, evolving, changing slowly over billions of years. Pluto does not rush. It does not announce itself. It simply continues, moving through its long orbit, breathing its thin atmosphere, reshaping its surface grain by grain. In a universe that often feels violent and overwhelming, Pluto shows us another kind of story, one of patience, of subtle energy, of quiet persistence. It reminds us that not all change is dramatic, not all importance is obvious. Some worlds matter not because they dominate their surroundings, but because they challenge how we think. Pluto changed how we define a planet. More importantly, it changed how we define a world. And that shift will shape how we explore the universe from here on. As New Horizons continues its journey outward, Pluto remains behind, not as a footnote, but as a turning point. A moment when we learn that the edges of the solar system are not empty. They are simply waiting for us to look again, more carefully, more humbly, and with better questions. And tonight, as Pluto continues its slow path around the sun, unchanged by our debates, it reminds us of something simple. Understanding does not come from labels. It comes from listening. Pluto keeps moving through the dark, quietly doing what it has always done. And for now, that is enough. Far beyond the warmth of the sun, Pluto continues its slow journey. Nothing dramatic, nothing urgent, just motion. Pluto completes one full orbit around the sun every 248 Earth years. A single year there lasts longer than many human lifetimes. Tonight, Pluto is still moving along that path. Quietly, steadily. Its surface remains cold and bright beneath distant starlight. Its plains of nitrogen ice continue their almost invisible flow, rising, sinking, reshaping themselves centimeter by centimeter over centuries. The mountains of water ice stand where they have stood for ages, not rushing, not collapsing, strong, patient. Above them, Pluto's thin atmosphere still lingers. Nitrogen and methane drift gently, forming delicate layers of haze. Molecules rise from the surface, then slowly settle back down. A breathing cycle that takes generations to complete. Nothing about it demands attention. It simply continues. Pluto does not know it was once called a planet. It does not know it was reclassified. It does not react to debates, definitions, or expectations. It moves because gravity guides it. It changes because physics allows it. And it does so without effort. While Pluto keeps moving, you don't have to. You've already followed the journey. You've seen how a distant world surprised us. With mountains where we expected flat ice, with motion where we expected silence, with chemistry where we expected emptiness. There is nothing left to solve tonight. No conclusions to reach, no answers you need to hold on to. Pluto will keep its secrets safely beneath the ice. Its hidden ocean, if it exists, will remain dark and undisturbed. Its atmosphere will continue its slow exchange with the surface. Its orbit will carry it onward, just as it has for billions of years. And none of that requires anything from you. You don't need to remember the numbers. You don't need to picture the landscapes. The universe does not ask you to stay awake. It asks nothing at all. In this moment, the solar system is calm. The planets follow their paths. The distant worlds remain in shadow. Space itself is quiet. Pluto is still out there, small, distant, and complete in its own way. And here, where you are, the day is finished. Your work is done. Your thoughts can slow. Just as Pluto drifts through the cold, steady and unhurried, you can let your breathing settle. Nothing needs your attention now. The universe will continue exactly as it should. Whether you are watching or resting, Pluto will keep moving. Its atmosphere will keep breathing. Its surface will keep changing far beyond the reach of sound. And you can rest. You don't need to follow the orbit. You don't need to stay curious tonight. Everything important is already in motion. So let the darkness be gentle. Let the silence stretch. The distant worlds are doing their quiet work, and for now, so are you. While Pluto continues its long journey through the dark, you are safe, still, and free to sleep.